Hi, my name is Daniel. I am a C++ software engineer and I will be conducting this course regarding the C++ standard template library. During this course, you will learn the key concepts of the STL library as well as gaining experience practicing it on real-world problems. We will cover both the basis of the STL and multiple optimizations that you can bring to your programs. Okay, let's dive straight into it.
Hi everyone, and welcome into the first video of this course in which we will prepare the environment for the following lectures. Thank you again for being here with me. And as far as tools are concerned, we will only use CodeBlocks. It is a free and open source IDE, which we will use because it is very easy to install, very quick setup, and after that in a couple minutes we are ready to start coding and learning what the STL can do in C++. The only thing that you need to do is just type CodeBlocks on Google or just go directly to codeblocks.org. In here you will find a downloads page, and then you can just go to binary releases, and now depending on the operating system you'll have here for Windows, Linux and Mac OS. While I'm using Windows, I can, for example, recommend you to get the no setup zip. So if you don't want to do an installation, we can just click it here. Be careful when you are downloading to download the version with the compiler. It's very important. So this one if you are using 64-bit, or any of these two if you are using 32-bit Windows. And right here we will select portable zip including compiler. We will wait for download to finish, and then we can move it here into our dedicated folder. Pretty straightforward. You just extract the zip in here. The process is similar regarding of no matter the operating system, so it should be very easy for you to get it installed. And it is if you took care of selecting the includer compiler version, you'll be ready to go in a few minutes. Just wait for your computer to extract all the files. Shouldn't take long. And afterwards we'll write a very quick program so that we can make sure everything works alright. It compiles, it runs your code, and you won't have to deal with any issues later. Okay, awesome. Right now search for codeblocks.exe. Actually you can run it directly. It's one of the fastest tools that I also use on a daily basis as a software developer engineer, because if you want to, for example, do a quick test or check a quick piece of code, it's one of the fastest programs to do that. That's why I also chose as the main and only tool for this course. So right now, as far as testing is concerned, let's write a quick program in C++. We'll save it as test1, for example, .c++. We will include IOStream for input-output capabilities, and we can write directly into our main function. From the standard namespace we can call the cout. It's a live, like this, and then an end line. Yeah, I should call it standard end line, and the return 0. And if we manage to do everything right, yep, we have it here. If by any chance sometimes CodeBlocks asks you, you may see a window pop up that tells you to select the compiler. Just click on the first one, the Ming W, and press the button set as default. It should go straight forward. It didn't ask me, it didn't ask this time, but it might. So right now we are ready to start learning about STL, and I'm looking forward to seeing you into the next video when we will discuss both theory and code regarding what containers can do and how you can use them practically to solve real world issues. Thank you very much for watching, and I'll see you in the next video. Bye. Round 5. Fight. Hi, in this lecture we are going to talk about STL fundamentals. We will introduce the basic theory and basic notations that we are going to use and talk about in the following videos. So you might be wondering, basically, what is STL? And STL stands for Standard Template Library. It incorporates multiple class templates which provide optimized implementation for different data structures. So basically we are going to use STL as optimized classes that we will need, and we don't want to implement from scratch. We'll call these classes containers. Okay, so let's cover containers. Containers are basically holder objects that stores collection of other objects. So as we can make a class that can incorporate, let's say, an int and a char or a string, for example, this is basically a holder object. So containers are basically classes. So from now on, whenever I talk about containers, I'm talking about a class from the STL library. They are implemented as class templates, which allows for great flexibility, and we'll also cover all the main methods that are already implemented, and we are going to use them excessively. They also take care of the storage space of the elements and provide useful member functions to access them directly or through iterators. One very important fact, you might be wondering, what is an iterator? Well, basically, iterators are really easy to understand. They are designed to manipulate containers, to traverse them in any way, and they are reference objects that are very similar to pointers. Most likely, you can say that they are the more natural way of working with containers, but not the only one. We are gonna use also basic operators like assignment operators from C++ standard and iterators to go through this type of containers. So let's cover the first container, and we are gonna apply all this theory there one by one, and we'll cover down and break down all the methods available. Welcome back, everyone. Right now we will start our first practical lesson in which we will start writing some code and applying the theory that we've learned so far. We will tackle all that we've learned and present the theory on the vector class, or better said, the vector container. And afterwards it will be much faster going through other containers types, and it's gonna be so much easier to understand. So it's very, very important to get the basics done. Alright, let's firstly include IOStream for input output, and the first container that we will cover being the vector. We'll be using namespace standard for coding speed, and right now in this lesson we will think of the vector. We will make visual the differences between an old C version vector and our STL vector. So basically what we need to have in mind is that our vector, our container, has two very important aspects. Firstly, we can think of it as the classical, it's a dynamic allocated vector, so we'll have to allocate memory, and either through the reserve method, or it will allocate automatically if we just push back elements at the end of the vector. And afterwards, very important, we always have the size of the vector. Okay, so this method size always returns the vector's number of elements. So right now, let's say this is our vector. I'll call it v, and we're gonna make a vector of ints. So let's declare our vector.
vector of ints. Being a template class, right here we can make basically a vector of any kind of data structure. So for example, we can have here characters or strings or any structure that we may define, classes and so on. But right now we'll be using a vector of ints. And basically we will have here our vector dynamically allocated, and we're also gonna have the size of it. So right now the size is 0. Let's push back a couple elements on the vector. And we can push back, let's say 10. And then seeing the size, so we should get a 1 and a return 0 for good practice. Alright, as you can see right now we have the first element in the vector, this 10. Let's push back more elements, 15 and 25. And right now we have all these 3 elements into our vector. So let's represent it here visually as well. So we'll have 10, then 15, and 20. Okay, and we know we have a size of 3. We can traversing the vector of printing it or making any other operation also in the old-fashioned way, so just iterating through it like here. Let me just comment this line of code. So we can make a for loop, declare our I starting from 0 and being less than v.size, which will always return the numbers of elements or objects in our vector, I++, and we can, for example, print our elements and then a white space so we can get a more clear view of them. Let's run this code. So right here we have our elements exactly as shown before, and right now let's do a classic operation. Let's add a custom number of elements into the vector, putting in inside and then getting them printed on the console. So we'll also call, for example, int number of elements. Let's request this number of elements. Yeah. Scouting how many elements do you want? Okay, we'll request the user to input an integer into this variable, and right afterwards also gonna make a similar for loop. So starting from I with 5 from 0, less than number of elements, I++, and right now we're also going to need an auxiliary integer. We will read our number into this auxiliary variable and then pushing it back at the end of the vector. Alright, let me comment this real quick. And right now we are reading a vector and then printing it. Printing our vector template class. Okay. So how many elements do we want? let's call it 5 elements, and then 1, 2, 5, 7, 9. And right now our v dot size will be 5 because we have 5 elements, and we are printing it in the old-fashioned way. Okay, so keep in mind the first element is always v of 0, the second element is v of 1, and so on. This is v of 2. So if we have, like here we have, for example, 3 elements, the last element will be v of 2. So if we have n elements, the last element in the vector will be v of n minus 1. Very important thing to remember. Moving on. Right now, we also mentioned iterators earlier. So we can also traverse a vector through an iterator. For this lesson, let's also cover the printing of a vector using an iterator. Old way, and right now we will have the same operation, printing our vector the STL way, let's call it. So for this one, we are going to use an iterator. We'll call it it, and right now it will be very important to use these functions right here, which begin returns an iterator to the first element of the vector. So let's also think about it for this one. Okay, so begin returns an iterator to the first element of the vector. Again, you can think of the iterator like a pointer. It has very similar properties to a pointer. So v.begin will give you an iterator pointing here to the first element, to the v of 0 element. And then v.end returns an iterator to a sentinel element after the last object in the vector. So for example, right here, if we have 3 elements, we will also have an empty element right here, which is going to be v.end. Okay, so how do we use these ones to go through a vector? Well, we're also going to need a for loop. We'll initialize our iterator with v.begin. Okay, because we want to start at the first element of the vector. When do we want to end? When, well, we want to print this one, move to the next one, print it, move to the next one, print it, and then when we reach v.end, we want our loop to end, so we know that we finished our vector. So right here we will write our iterator is different than v.end, okay, and then increment our iterator, and then print the value of the iterator. Is very important. Do not forget to put the star right here, because an iterator is similar to, let me put the white space. Okay, the iterator is very similar to a pointer, so we want to take the value from this reference, because also v of y is equivalent to star v plus I. So basically v is a pointer, we are incrementing its I values, and then we are getting I positions, better said, and then we are taking the value out of this position. Okay, so very important thing to keep in mind. And right now let's see if our two prints shows the same thing. Let's also see out an end line right here. And let's read a bigger vector, let's say 7 elements, and all the number from 1 to 7. Okay, so we have them, yeah, also would have been a great idea having an end line between them. Let's say 3, 10, 15 and 25. It's our original vector. And as you can see, both behave the same way, but there are different ways of traversing a vector and manipulating it, which is going to give you much more flexibility when solving problems. So right now we covered reading and writing the vector through the old way, the C way, and the STL way, the iterator way. Okay, thank you for watching, and don't forget to come back for the next video. Welcome back everyone to the next lecture of this course, when we will talk about the array. Array is a sequence container, and it basically just represents a static contiguous array. So apart from the vector, we have another possible competitor for representing multiple elements, multiple type of data structures, of data types in some sort of list. And what is the main difference about them is that the vector is dynamically allocated, so we will find it in the heap as far as memory is concerned. In the case of the array, it will be statically allocated, so it will be allocated, its memory will be found on the stack. Apart from these differences, why would you want to use, for example, the array container and not the, let's just say, basic C vector style? So just declare it a vector like this, or a pointer, and make it a vector. Well, basically because C style vectors can be somehow diluted into pointers, and that's one disadvantage that you might want to get rid of. The array container is more reliable, is actually more lightweight than the old-fashioned C-style vector, and helps you write code more easily. So in your future projects, it would be better if you took advantage of this array container more and give up the old style C programming habits. So without further introduction, let's get right into code. It will be a very easy lecture. I think there will be nothing that will shock you greatly. We will only include IOStream and array for this program, just for reading and writing things to the console, and then the array container from the STL. Going into our main function, for declaring arrays, you just write it exactly as we did at our vector class. You just type array, and then between these smaller greater signs, you just have to write it the type of data you want in your array. So we'll use a very simple array of integers, and right here you should write also a second parameter, the number of elements, so that it directly allocates it faster, and you can have everything set from the beginning from allocating your array. So let's make it a vector of 5 elements. We'll call it just A or AR, A better, and we can directly set numbers in here, for example 1, 3, 5, 9 and 7. As far as traversing the array is concerned, it is just
exactly as a normal vector, so you won't find any difficulty in using it in your code. You just have to change the declaration, and then you also don't need any additional variable for its size, because you have a dot size exactly as we used at the vector example in the previous lecture, plus I. And again, now in your functions you won't need anymore to pass in any additional variable regarding the size of your vector or anything like that. You just change the declaration and you have everything you need in your vector, in your array class, in your array object. Actually, let's see out the object, actually the element, with a space in between each other, and a return 0 to see for sure that our program ended running successfully. And as you can see, we have our array in here. It's a very easy way, the most basic way of organizing your data, and with this class, if you use this container and not the previous way of declaring static strings of elements, you will have your code way more optimized, and your runtime you'll notice that will be slightly lower than what you have experienced before. Let's also do a quick input-output style. So I'll copy this 4 and paste it in here. So right now we will ask the user to give us the numbers that he or she wants into the array. So counting enter the 5 numbers, and let's just see this working through. You can just write 1, 2, 3, 4, and 5, entering, and we have them printed in here with this for loop. Sorry. It is not a container that will greatly help you, for example, in your interviews or in any specific type of problem, but it's worth mentioning because you can, for example, do very quick tests using this class. You just can declare an array very quickly and then do any sort of test that you want on it. And I would definitely recommend you to consider using it more often into your future projects and into normal code. So right now we have just finished the sequence containers chapter. The next ones will be a little bit more challenging, and I will also provide you with multiple problems so that you can get a better understanding of how these containers are used in real world problems and how you can start applying them and learning how to deal with them. In the meantime, if you want to practice this more, you can just start by writing very simple code, or you can implement a very basic sorting system on this type of array. If you want to do it by yourself, you can just pause the video, and if not, if you want to see how this is done, well, it's basically just take any other algorithm, any other sorting algorithm that you have so far, and just change the declaration of your vector with this array of A, and everything should go straightforward. If you want to try the simplest sorting method possible, which I would never recommend you to use, is writing a double for loop
like this. We will start it I at the beginning, this I variable at the beginning of the vector. We will go to a dot size minus 1 plus plus I, and in the second for we have to start our j variable at I. J should be lower than a dot size this time, and plus plus j. And if a of I, and I forgot the a, is greater actually the n of j, then we should swap these two like this. I will also need another integer in here, temporary variable. So temp is equal to a of x, just swapping these two variables. We also have a swap function, but this should seem just more familiar to you than using more additional functions. In this array class, you will also find way more functions implemented in it that you can also research by accessing the documentation link that I've provided below. But for you to get started with it, this is just everything you need to know in order to start using it in your code. And right now, if we run it, and let's give it some random order numbers, 4 to 5 to 4, 3 and 1. Right now we have it sorted. So this is just a small demonstration that you can take any other previous piece of code that you have ever written in C or C++, sorry, and just change the variable, and everywhere you can put a dot size, the object dot size, in which we have the length of the array stored. Thank you very much for watching, and prepare yourself for the next chapter. They will be a little bit more challenging, and the fun has just begun. Thank you again, and see you in the next video. Bye. Hello everyone. In this lecture, we will start talking about container adapters, which will provide us with a different interface for sequential containers. They are also much easier to understand and use. The first one that we will talk about will be the stack. The stack is a LIFO data structure, meaning a last in, first out. And we should better try representing one before explaining anything. So we should think of it like a box in which we can add objects, and in our case, let's say basic integers. We can push objects into it, a 3, and then let's say a 5, and afterwards a 1. And we cannot access the items directly. So for example, if we want to take out the 5, we will basically need to get rid of the 1 first. So if we want to access any of these elements, we have to first pull out all the other above, all of the objects above it. So there's one way of putting the objects on top of the stack, and we can only take objects from the top of the stack out. And we will see how this translates into code. So this visualization is very, very good for your learning. Try practicing it the first couple of problems that you solve, and you'll find it very easy to use in no time. Alright, firstly we are going to include iostream and stack. Using namespace standard. And see exactly how a stack behaves. So let's declare a stack of integers and push a couple of elements into it. S.push 3
then a 5 and a 1, exactly as we drew earlier. And let's also create our printing function. So void print, which will take only one argument, our stack, which is to be printed, of course. And in this case, we will use a lot these 5 methods that are built in into the stack template class. So the fastest way of printing a stack is basically checking it if it is empty, while s.empty is not true, so basically the stack is false. It means that we have at least one element in our stack, and meaning we can print it and then take it out. So we will print s.top, which returns us the upmost element, an empty space, and then we will pop the element that we just printed. And this will repeat until our stack is empty. So in this case, it will print 1, then it will take out of the stack. 5 would be the top, it will print 5, it will pop out, and then 3, and after 3 has been popped out, the stack is empty. Let's also add an empty line, an end line at the end of our print. And let's see it in action. Build and run. While s.empty, of course I forgot the parentheses. My bad. So exactly as we've seen before, we take the 1, we print it to the console, and then we pop it out of the screen. Then 5 would be the top, here comes it, and 3 at the end. Again, if we want to access, for example, 3, and we know it's the third element of the stack, counting it from top to bottom, we will first have to pop up all the elements above it. So s.pop, let's say cout searching for 3. So 3. We will pop out 1, then we will pop out 5, and right now if we can directly cout s.top, and we should see our 3 on the screen. Rebuild and run. And we got it. Again, we took all the objects above 3 until it becomes the upmost object, and then we can take it out. Please keep in mind it is a very important data structure, so check again the documentation that I've provided and try to solve the recommended problems below. Thank you for your patience and see you in the next lecture. Hello everyone and welcome back. In the previous video we have discussed about the stack. And right now we will tackle one of the most common problems that you will most likely get at interviews regarding this data structure. So basically it is called the parentheses problem. It states something like this. Basically there are 2 versions of the problem. They are quite similar. We will tackle the simpler one because it will be a lot faster for you to understand it, and then for the more complicated version you basically just need to add a couple if statements, and well, that's everything you need to know, but we're gonna discuss it at the end of the video. So what the problem states is that you have a string of parentheses and you have to write a function in order to tell whether the string is valid or not. And a string is considered valid if all the parentheses close themselves. So let's take a quick look at a few examples. So let's say this is a valid example. Well, let's draw them up a bit more beautiful. This is a valid example. This is not a valid example because this one's closes like this and this one remains unclosed. We do not have an additional closing parenthesis, so it's not valid. This one is a valid one because these two close each other, these two close each other, and after that will be the bigger one that closes, so it's alright. Whereas this one is again a valid one because this one, these two parentheses close each other, these two will close each other, and right now if I add one more, well, this string will not close anymore. Let's take one more. This is by default not is an invalid string because there's only one parenthesis and we don't have anything to close it. So we may start finding a rule. Basically, if we have an odd number of parentheses, then we can be sure they won't close each other because you basically need two parentheses to cancel each other, and if you have an odd number, that means there will be one left and it won't matter if it's an opening or a closing one. So how do we use the stack in order to solve this problem? Basically, let's first take a quick look at what we learned so far and how does a stack actually works. So let's imagine our stack right here, and let's remember the basic rules. So we can add an element to the stack. Let's take numbers for now. We can add number 1, we can add another element, number 2, let's also add a number 3, and after that we can pop an element from the stack. So we can only add elements on the top of the stack, and we can pop them as well from the top of the stack. So if we get an element out, it's gonna be 3. If we take another element out, it's gonna be 2. Then if we add a new one, we'll have here, let's say 4, and if we pop it, 4 goes out. So in order to visualize this problem, we will do the exact same thing, but imagine the stack horizontally. So let me draw the stack right here, and we will imagine that we are pushing and popping parentheses in. So for example, let's take this bigger one because it will be easier for you to visualize it. So this is the first parenthesis, and the rule is very simple. If it is an opening parenthesis, that means push. If it is a closing parenthesis, that means a pop. We only want to keep inside the stack the opening parenthesis, because a closed parenthesis, what it does is basically closes one opening parenthesis. So basically, if we have here an opening one and here a closing one, they cancel each other. So if we add an opening one and then there's a closing one, we just need to get rid of this one because we don't need it anymore. So let's do it on this example. Okay, so we have a closing parenthesis, so we are pushing it onto the stack. Then another opening parenthesis, so we are pushing it again into the stack. Then we have a closing one, which means pop, so this one pops out. After that we have a closing one, an opening one, so another element pushed into the stack, closing one, so this means a pop. And then here again a closing one, which means we are gonna pop it out. And right now our stack is empty. What does it mean? It means that all the parentheses closed themselves and that the string is valid. Of course, there are some edge cases. For example, if we only have this kind of parentheses, they will only get pushed into the stack, but then never gets popped out. So basically, if our stack is not empty, that tells us directly that not all parentheses have been closed and the string is not valid. As well as if we have this kind of example, we push the first parenthesis here, everything's right so far, we then pop it out because of this one, and then we have another pop. And if we encounter a pop when the stack is empty, that means that the string is not valid, because it means that we have an closing parenthesis but no prior opening parenthesis that can close it, that needs to be closed. So we have to take care of these examples of these side edges that are called in our code. Alright, let's start writing the code. So we'll save this for later and start writing, let's say, the parenthesis problem. Stack solution. You may offer multiple solutions to this problem. I think it's big enough. Yes. So we will include IOStream to have input-output capabilities. The stack from the standard template library, and I'm also considering including the string to quickly read our input. Alright, let's write a quick basic main function. So we can scene dot, let's declare our string first. String as str, scene dot get line of str, and right here it's not compulsory to add a number, but we'll just put it to as a default one. And right now let's do our function, because we needed everything clear, and doing a function would make the code look a lot cleaner. We can declare it as a bool, valid. As an argument, we only need our string of parentheses, and then we can start solving the problem. So if we look again at our solution is entirely based on the use of stack and its properties. So we will declare our stack of characters, because the parenthesis is a character, S, or no, I don't think it's no issue in that. And then we can make a for loop for our string. Let's say we are gonna start at the beginning of the string, we go to the end of it, and then we add 1. All right. And right now we have to consider the beginning of any possible string. So first, let's take a quick look at the first element. Do we have any sort of kind of edge cases that can apply here? It's a very important question we need to ask ourselves when we do any problem. So whenever you have a vector or some sort of rule that you found in order to solve a problem, first consider that most likely you might have edge cases at the beginning or at the end of your array of characters or vector or anything. So at the beginning everything is quite straightforward. I mean, if we have an opening parenthesis, we just push it. If we have unclosed parentheses, technically we have to pop it, but always, as we discussed earlier, we have to make sure our stack is not empty. If our stack is empty, then we can directly return false, because we have the guarantee that the string is not valid. So we're gonna do an if str of y is an opening parenthesis, let's add some spaces, then it's quite simple, s dot push the if element of our string. All right, else, so in this case we know that it's a closing parenthesis. We also have to make another if statement in order to check if the stack is empty. So if stack dot empty, if it's true, I mean if it's different of false, then we can directly return false, which means that our string is not valid. Else, if it is not empty, well, that means that we have opening parentheses in our string, and right now we are free to go to pop it out. So s.pop should be enough. This will cover the entire string, and we'll go until the end of the string and tackle every single item. Right now, after we finish the string, we have one more question to ask, and it's actually the edge case that we discussed earlier. If we only have opening parentheses and they stack up into the stack, then we have to make sure that when we finish constructing our stack and going through the string, our stack is empty, because it is our indicator if the string is valid. So again, we will do the exact same string, the exact same if condition, sorry. If stack that dot empty is true, then this time we return true, because we finished traversing the string, every parenthesis close themselves, and we have true. Else, it means we have further closing parentheses that have no match, so we will return false. Right now we will test our function here. So let's see out valid of our string, and we'll do a couple tests on quick strings. I also forgot using the standard namespace. Well, let's see if we wrote the code correctly. Oh, most likely oh, sorry, my bad. I was thinking I was thinking of reading it as a pointer to char, but yeah, I changed my mind at the very first second. So yep, we can just directly read a string with sin. So let's try a few of the examples that we talked about. So this should be valid. Yep, perfectly. Right now, let's get a few more complicated examples. So for example, we open and close parentheses, then we open two, we close the first one, and another one is opening. So right now in the stack, we should have these two. We are closing this one, and we are closing the second one, and this one should be true. perfectly. Let's try a quick false example. Yep, it's false. And the most obvious edge cases, if we only have opening parentheses, and let's also add a couple of closing ones. Definitely not valid, perfectly. And also just a closing parenthesis, not valid. All right, right now for optimization, we might also add the rule that we discussed at the very beginning of the video, that if the str.size is an odd number, then directly we can return false. And let's also pick this one in here. If modulo 2 is different from 0, which means is 1, which means this parenthesis is an odd number, is 1, we can directly return false. And it will be a lot quicker. So right now, if we say something like this, then when we go into the function, it won't traverse the entire string and check for every single parenthesis and ifs and everything else. It will just check if the size is an odd number and then return false directly. And this kind of problem, it's usually one of the opening ones that you may find at an interview. It also teaches you very well the basic use of stack and how you can use it to visualize quite simple problems that just requires you to make a couple moves, like pushing and popping. Right now, I think everything is quite clear, and we can go on into discussing the little bit more difficult version of this problem, which you'll see that you'll manage right away without any issues. It's very important because in most cases you might find that type of problem at an interview, just to add a little bit of complexity. So the problem tells us it is the exact same requirement, but you can have multiple type of parentheses. For example, strings like this, or strings like this. Usually there's only these three types. Let's also try another test, more complicated one. Alright, these two are definitely valid because you can see each parenthesis gets closed sooner or later. This one is not valid because it's a different type of parenthesis. What's the difference and how we can make our code also run this type of problem, this type of variation of our problem? And we can do it very quickly. Right here, when we enter, if we have, for example, a closing parenthesis, we directly return false. But let's take it the other way around, actually. It's enough just to think of this problem as we thought of our variation earlier. So firstly, you have to tackle the opening parenthesis case, which will require here a little bit more if statements. So we'll check if it's in opening parenthesis of this type. Let's say type 1, type 2, and type 3. And if it's an round parenthesis, then we push it to the stack. Actually, we can directly check if it's an circle parenthesis or a square parenthesis. Sorry, I forgot to also add the character itself. Or this kind of parentheses. Yep, right here. And if it's an opening one, we just push it into the string. But right now, if it's a closing one, then we have to add a few more if statements, because this example is actually the best one you need. You have an opening parenthesis and then a closing one, and this closing one cannot, well, cancel this one because they are not of the same type. So this is the only thing that we have to check. Right now that we made sure, okay, if it's an opening one, it gets added into the stack. Right now, if we got into this else, it's a closing one, but we also have to make sure that they are on the same type. This if statement stays, so if the stack is empty, directly return false. No further explanation needed. But if it's not empty, well, at this else we have to make a few changes, and we have to check whether the top of the stack is the opposite of our parentheses here, because let's take this example, and we make our stack. This one gets pushed into the stack, this one closes this one so we can pop it out, then it comes the square one, and here we have a round parenthesis, and this one is not of the same type as this one, so we have to make sure that they're on the same type in order for us to be able to initiate that pop function. So if the top of the stack is a round parenthesis, and that is not an end, definitely not an end, and our current character is a closing round parenthesis, well, everything's right. But we also have a few more cases, the other types of parentheses. So we can copy this double statement and then put an or between them, and then another or, because we have to make sure if it's this type and this type, everything's fine, we can pop, because this one closes this one. Right now here is the square one, and of course the one that closes it, and the last one, we should not forget it. Yep, if we have any of these three cases, then we are free to go and continue with our pop function, because we want to get that element out of the stack. And if this else, and if this statement is not to be found, none of these cases are met, then basically we are in this scenario where we have two parentheses that cannot close each other and they are right next to each other, so we have to unfortunately return false and tell our program that the string is not valid. And even though we might have here, for example, no, I don't want to save it, and even though we might have here something like this, it will also go invalid, it will also return false, because let's actually also follow the code for this example. So an opening parenthesis, very easy, we push it into the stack. Another opening parenthesis, no problem, we just push it over, because we just entered this if, only opening parentheses, they get pushed. Then we have our first closing parenthesis, so we check if the stack is empty, and it is not, we have two elements. Afterwards we go to this else and we check whether we have one of these three cases, So it is definitely not this one, because the top of the stack is not a round parenthesis, neither a square, so we only have this one here. And we check that our character from the string is actually the exact same type as this one. I mean, these two can close each other, so we are free to go with s.pop. This one gets deleted from the function, from our stack, and afterwards this one comes in. It's not an opening parenthesis, so we go to this else. The stack is not empty. We have one more element here, and after that we check any of these cases, and we see that s.top will be this square parenthesis. So we are in this scenario, but we also have an and here, that our character is a closed square parenthesis, and it is not our case, which means we directly go into this else and we return false. Right now I just realized that we have s.top is a function, and I forgot adding a couple parentheses here, which would make it an invalid string for our problem. Let's also try this code right here. Okay, our beloved example from earlier should definitely return false, and it did. And right now let's add something more tricky. Can I get some inspiration from here? Yeah, we will try to reproduce this one. So not what I was expecting. Write this, round ones, and yep, I hope I wrote it right. Yes, I did. And the code seems to be backing me up, saying that is all right. Let's also try a few more ones, just for testing purposes. Let's try this one. So right, this you can also play with it as long as you'd like. I will attach both programs to the description of this lesson. True, and also another one that's invalid, so we make sure everything's in order. Although we somehow checked this type of inconvenience. Yeah, false. Spend a little bit of time digesting this code. Try making them some notes. The best way of understanding and thinking these problems is by taking a piece of paper and a pen, writing down examples, writing down how you think they can be solved. Try doing it one by one. I mean, taking one parenthesis at a time, considering what are the cases, what might come next. Start building your strategy, and after that, after mastering this solution, it would be great if you would like to implement it yourself. It would help you very much in problem solving, and if you get stuck, you can get back to this code. If anywhere you don't feel like you know what's going on in your stack, you just use the print stack function from the previous lesson and just print the stack at any stage or character in your string, so you will perfectly understand for each character how does your stack look, what that does your stack look like, actually, my bad. And good luck trying to solve this problem by yourself. Watch this video twice if you feel like you have some misunderstandings and you want to check it out one more time. It's perfectly fine. It's normal when you start working with this type of data structures and their implementation in the STL library. Thank you very much for watching, and I'll see you in the next lecture. Have a nice day. Welcome back, everyone, to the next lesson about container adapters. In this lesson, in this lecture, we are going to talk about the queue. The queue is a FIFO data structure, means first in, first out. So it's a little bit different from the stack. So if you remember, the stack was a LIFO data structure, meaning last in, first out, and we could push element into the stack, but only get out the up top element of that stack. When it comes to a queue, you just have to see it as some sort of tunnel. Let's write here queue, and it is very easy to visualize. You can actually think of it as the queue from your local supermarket. You know, when where there is a stand and afterwards people are coming and they are getting out through here. So when we have push, we can push people in the queue in here, or objects, or any other type of data into our queue, and when we pop it out from here. So if you remember from the stack, we were popping this way and this one was blocked. Right now we are popping things from here, so we can push here an element, let's say 1, we can push another element, 2, another element, 5, and if we pop 1 first, then 2, and then 5. If it were a stack, it would have been 5, 2, and 1. These data structures very easily helps you visualize data, or take care of the data in some sort of chronological order, meaning that if an object has been staying in the queue for a longer period of time, then for the longest period of time, then that element is certainly right now the first element of the queue. So it gives you some sort of efficiency in dealing with data, and it might come in handy into a lot of problems. This data structure is usually used in problems like the theater problem, where you have a certain amount of theaters, like 5, 6, and then you have certain plays that you have to organize, and based on a routine you have to say whether it's a valid one or not. And at this particular kind of problems, a queue helps you very easily visualize your data and manage it the fastest and most efficient way possible. So right now, getting into code, let's see how it happens exactly. Again, same as the stack, most of our operations take off one time. For example, erasing an entire queue or something like that, or traversing it, printing it, all would take off n, but apart from that, most operations do off one. So starting our code by including IOStream for input-output capabilities, and of course our queue container from the STL. We will use, as always, the standard namespace, so you won't have to call it every single time. And right now we can declare a queue, as we've learned so far, as any other container, and we can make a queue of integers, of numbers. In this case, we're going to call it actually queue, and we can populate it. Let's push a few numbers into the queue, 1 and 3, 7. Okay, let's write a quick function that would print our queue. So void print, it will only have one parameter, that's the queue that we want to print. And while we are going to use queue.empty, That's how when you are dealing with container adapters, for example, most likely stack or queues, you can use this function abusively to constantly check whether your container is empty or not. So for example, if a container is empty, there's no element to pop, so you might get into some issues or unexpected behavior due to that fact. If our q.empty is not true, we want to print q.front, which will be the first element from the queue. So it will be actually the oldest element that we inserted into it. So let's build our queue in here as well. 1, 3, and 7. 1 being the oldest element will be the upfront one. And after that, q.pop, so we can pop the one out of the queue, and we have the rest of it remaining here in order to continue printing and traversing it. And yep, that should be it. q.empty. All right, let's call it print of q. My bad. Yep, just realized here I have to place a not, because we have to go back into this while q.empty is not empty, and we could also have added here a backspace, a space between the characters. So as you can see, we have 1, 3, and 7. Adding here an end line would be actually better. So after we print the entire queue, we'll go in, we'll print the end of the line, and then we'll go back to the following line, because right now I want, for example, to pop the oldest element from the queue, the first one that has been pushed from the ones that we currently have. So we would only now get 3 and 7. Print of q. And as you can see right here, after we push these 3 elements, we have all of them in the queue. After we called q.pop, we got rid of the oldest element, and then when we print the queue again, there's only gonna be 3 and 7 left in here. If we were to push another element right now, it would be after the 7. So let's consider popping that 3 as well. And right now, q.push 0 and print of q. Let's check the code right now. What is happening? So before watching, let's find the answer by ourselves. We have pushed into the queue 1, 3, and 7. We print the queue. All right, so we should have 1, 3, and 7. Right now we are popping the 1. Okay, we got rid of it. We are printing the queue 3 and 7. You can easily read it by just taking all the elements in this direction. Then we are popping the 3 here, so we also get rid of the 3. We push a 0. Okay, so here we'll have a 0, and then printing the queue, the only elements left in the queue are 7 and 0. We read them like this, so we're gonna have 7 and 0, and it's exactly the output that we got. For this particular data structure, you will encounter it in very specific problems, and truth be told, it's not found in day-to-day programming, although it's very important to know it, because in certain situations or particular questions, it might get you out of the trouble by having your data a little bit organized in this way. And if you have to do any assignment, or you have some set of data that is based on a chronological requirement or feature, the first thing that should come into your mind is your queue, because rather than sorting or whatever, the queue will take care of this by itself. Because when you push an element to the queue, you basically like giving it a timer kind of thinking. You can visualize it like this. You are giving it a timer, and the oldest element into the queue will be the first one popped out. So if you need tasks to be, for example, taken care of in the order that they were introduced, just use a queue and it will make your job a lot easier. Thank you very much for watching, and can't wait to see you in the next one. Thank you. Alright, in today's lecture we are going to talk about associative containers. They implement sorted data structures that can be quickly searched. The first container from this category that we will cover is the set. It is a collection of unique keys which is implemented as a balanced binary tree. One of its biggest advantages is that most operations, for example insert, find and erase, takes O of log n time complexity. Diving directly into code, we will see how exactly do we use this set in real life problems. So we will include standard input output stream and our set using namespace standard as well. And in our main function we will declare a set of integers, and let's insert a couple of elements. We can directly insert, for example, 3, 7 and 1. And right now let's quickly write our usual print function, which will take our set as a parameter and print it to the console for us. We will also declare here an iterator. We will initialize it with s.begin, which returns a constant iterator to the first element of our set. We will stop when we reach s.end. Again, is a sentinel, basically an empty element after the last element of the set, and we will increment the iterator, printing its value and an empty space afterwards. And let's end the line after our set is printed. Okay, so let's see. Our set right now. So we should have these values 1, 3 and 7 in this order, because again it sorts our values. Okay, right now let's, for example, erase an element. Let's say 3. So cout erasing 3 and end of line. s.erase 3, again in O of log n time complexity, and printing it to the console. And we can see 3 was erased. The only function, the only method here that takes O of n complexity is clear, which basically deletes our set. Apart from that, we will find it very, very useful in a lot of problems where we have a lot of searching and erasing to do, because we always have the guarantee that we have a balanced binary tree behind our set. Welcome back, everyone. Today we will continue discussing about associative containers, covering the map. What it actually does is that it stores elements in a mapped fashion. So basically each map has a key value and a mapped value. Basically it is a collection of key value pairs sorted by keys. One very important aspect to keep in mind is that inside of a map, keys are unique. So we cannot have the same key with different values. So for example, if I have a key 1 with value 20, for example, I cannot have another key 1 here. It's forbidden. Okay, pay close attention to this one because this is a very useful class template which can solve a wide variety of problems. And it is exactly how I want you to think about this. We'll actually solve a real world problem trying to map the characters in a word. And on the same principle, we can also map the words in a sentence and so on. So let's take tuna as our example word. And we want to map it. So as I've mentioned, we will have the keys, meaning the characters, one by one, sorted. So in the end, I want A with the value 1 because A appears only 1 in the word. Then the next one would be N with the value 1, T with the same value, and U with value 1. If I want, for example, to write it with 2 A's, then I will have here value 2 because I have 2 A's into the word. Alright, so let's see how we can do it. So we will firstly include all the requirements, IOStream. We will use the string class and also our map. Let's use the standard namespace by default, and declaring our map is very simple. We just call it map, and we give here the key data structure and the value data structure. So in our case, we basically want to map by characters, all right, and we want to count them. So we'll have character and int right here. So we'll map characters and we'll have int values, and this is basically how we declare our map. And we will also need our string. So let's simply read and write to the console our string to check if everything's alright. So tuna. Okay, so right now we are reading and printing it correctly. And let's start mapping it. We'll use a for to traverse the string from 0 to string.size. And we'll basically call map of the ith element of the string plus plus. Why are we using this? Because it's very simple. So let's take a look at tuna. Basically, we'll take the first letter, the first character, T, and we'll say map of T plus plus. So basically, here we are passing in the value, and this, here we are passing, the key, and here we have the value. So if T is not yet in the map, it will be initialized with the value of 0. So this is why we are writing the plus plus to give it a value of 1. Okay, so how it actually does is exactly like this. We take the T, the first character, our map is empty, and then we basically say map of t something. Okay, the map first searches, do we have a t? Well, not yet, because it's the first t that we encounter. So map of t by default is equal to 0. And when we are writing plus plus, it will take the value of 1 and it will add it right here. Actually, it will be the first element of the map, but when the other ones will came, it will sort them automatically. And this is very simple, creating our map. So we are going to write here mapping the string. And right now let's print our map to the console. For this we will use an iterator. We will start at the first element, map.begin. And of course we will stop at the sentinel element, which is located at map.end after the last element of the map. Incrementing the iterator, and right now we will be printing iterator first, which is the key of the element. Then let's beautify this a little bit, and then the value, the second element of the iterator, and maybe an end line after each element. So when we are traversing a map through an iterator, the first is the value of the map, and the second, the first is the key of the map, sorry, and the value is the second is the value. Okay, let's run this one. Let's write it tuna. And as you can see, we have exactly the map that we predicted before. And let's also call it with double A. And as you can see, we have our string mapped. It is also called a frequency map because we are basically counting how many times each element can be found, and we are practically determining its frequency. Keep in mind this is a very important exercise. Please focus on the problem, and also check this video twice if you feel you have any problems. Ask some questions and check the documentation. I'll see you in the next lecture. Hi everyone. Hi everyone, welcome back. In today's video we are going to tackle a very important type of problem that I've personally encountered in multiple interviews, and I do believe that studying more on maps will give you a huge advantage over your future interviews, because it's a data structure that I've personally considered and actually used at almost every single one of my interviews, and I'm sure it will help you greatly. So without further introduction, we will go directly into the problem. We have our test here. So what this problem actually requires us is to find the most used word in a paragraph. It might sound a little bit similar to the problem that we've already solved in the map lecture, but trust me, this is really important to focus on, and understanding the map and basically the frequency map and how it can get you out of all sorts of trouble, and it's a very quick way of solving a lot of problems will always be an advantage that you might want to use as often as possible. So we have this paragraph and we want to return the word that has been used the highest number of times. So in order to do that, we are going to do a map which words are gonna be the keys, and their number of appearances will be the value. So let's make a quick recap of how a map actually works. So if we consider that this is our map, let's write here a map. We have it stored like this. So we have a key table and a values table. So basically a map contains certain values which we can reach by using a certain key, and so on. And we will create the map in the following way. If we find a new word, for example this, let's put here a lower cap t. Okay, if we don't find any value for this, for the key this, we will add it into the map, and by default the value of it, if we consider it to be an int in our case, it's gonna be 0, but we will by default increase it to 1 because we already encountered this once, and every single time we will encounter this we will increase this value. So we just have to call map of this, and then it will return us the value. And we will do this for every single word. We're gonna add it into the map as our keys, and in the value field we will count how many times did we encounter that word so far in our map, actually in our paragraph. And in the end there are multiple ways in which we can do this. One of them is just traversing the map, but we should be better if we print the entire map so that we can see that it did exactly what we expected it to do, and afterwards just find the key with the biggest value, which is basically finding the maximum number into a vector. So pretty straightforward. Let's jump into the code. We will by default include iostream for reading and outputting, the map library as well, and this should be everything so far that we need. Standard namespace as usual, and right now into the main we will consider firstly that we read the number of words that we have in our paragraph. So we have an integer number of words which we will read, and then I also have to include a string because it would be a lot faster if we read them as strings. And right now we can just do a quick for loop in which we will read every single word and add it into our map. So let's declare our map first. So we need the map which has as the key data structure a string, and then an integer as the value, the type of data. Let's call it m for the moment. And right now we have to write multiple instructions in this for. So firstly we have to declare our string. Let's call this str, read it, and then we can just call map of str plus plus. What this basically does again is, where is it? Right here. If we have the key allocated. So for example, we have this map right here, this with the value 1. If the next word is this, then map of this will be 1. And if we just did plus plus, then the value will get 2. If our word is not this, and for example it is let's say by default it will have the value 0, and it will automatically increase to 1 because we just encountered it, and well, that's one appearance so far. Alright, after creating our map, let's declare an iterator. Better do it at the beginning of the program. Selecting everything, iterator, it, and we will start the iterator by initializing him with m.begin, which again returns an iterator to the first element of the map. We will proceed until the iterator has reached, or will actually reach, m.end, which is a sentinel after the last element of the vector of the map, sorry, and we will increase the iterator. So for example, if we have this map right here, what other words should we use? Actually word with the value 2. Map.begin will make our iterator point to the first element of the map, and map.end will make it point to a sentinel, which is basically a blank element after the last element of the map. So you can visualize the map of being made out of these 3 elements, and this is the size of the map. Actually, if we call map.size, it will give us 3 elements. But in the container code, we also have this blank node, which is again called the sentinel, after the last element of the map. Since we used an ordered map, these words will also be sorted alphabetically, sorry. But if we were to use an unordered map, they would just be in a completely random order. We will visualize both possibilities right away. So here let's firstly print the key, which is first, then a quick space, and then the second value, which is actually the value that we discussed earlier, and an end line. So right now everything should be in order. We should be able to see our map. We will write 22 words, and our words are here. Copy this and paste here. And you can see that we have every single word counted. So if we look really quick, we will see that the word the has been found 2 times, which would be here and here, and the word to has been found 2 times, here and probably here. Okay, for example, if we were to add 23 and we would put just one more the in here, let's quickly rerun this. Actually, I want this selected and copied. 23, copy paste, and right now we have the 3 times. Why is it so important to keep in mind this data structure? Is because basically what it does is it gives you some sort of let's call it quick statistics over a set of data in very little code, so you can write it even if you need some testing purposes or just to visualize your data a little bit easier, which may be common in C++. You can just do it a quick map, and then you can see it very clearly and have a greater look at your problem than just having the example row printed. And right now, in order for us to quickly finish it, let's have the it.begin here, and we will declare a maximum equal to it of second. So we will take the first element of the map, and its value, it's our current maximum. And right now, if we find any value bigger than this one, well, we will update our maximum. And let's consider if we want to return the actual number or the string, because if we want to return the string, we also have to declare it. So let's call it string solution. We'll leave it as sol it first. This initialization is no longer needed. Proceeding forward, we just need to put an if. If the current ID of second is greater than our current maximum, we just need to update it. And also to remember the word. And after this for loop, we can just print the solution, and if we want the maximum number of appearances in our paragraph. If, for example, we have multiple words, we can use actually, we should create a vector in which to put all the words that have this number of appearances. But let's take just a simpler example and check it on this one. So it should be our the from earlier, 23, and copying it. Yep, so we have the, which appeared 3 times in our map. What is one of the most relevant aspects of this approach is that you can use it in so many problems. It's actually becomes a habit of thinking of most problems as if you need a map, because a lot of times you might need to sort some values really quick and then get the most return one that has the most appearances, or for example right here, words in a paragraph or letters in a word that we described earlier in the first map lecture, or the number that's most used in a vector or anything like that. And you can do actually multiple sorting rules with map, or you can just use an ordered map if the complexity requires it. Actually, an ordered map works really quick. And Practice this kind of problem. Try thinking it for yourself, writing your map on paper, and then try to approach this kind of technique. Write your own code, and if you have any doubts, feel free to rewatch this video and get yourself comfortable with it. I also leave you'll also find more problems on which you can practice the map in the description of the initial map lecture video. Thank you very much for watching, and see you in the next one. Have a nice day. Hello back everyone, and welcome in today's video. Today we will start talking about unordered associative containers. Since we have already finished the associative containers part, this one will be a lot easier to understand. It's basically an extension of that. So today we will talk about unordered map, and you'll get in a couple seconds what exactly it does. So you should think of it as a normal map that just doesn't sort its elements by keys. So if we remember from the previous videos, we have not like that. We had the map which contains keys and values, and each value has a certain key with which we can find it. So we can have, for example, let's take a word, a string, and we have a map of characters and ints. So right here, if we were to insert into the map, let's say A, B, and C, then we would have the first element would be A with a certain value, the second one B, and the last one C. And it doesn't matter in which order do we introduce the items, the map will automatically sort them alphabetically. If there are integers, then of course the map will sort them in ascending order. Why are we talking about unordered associative containers? Well, the main answer is that they are a lot faster. So there might be a lot of problems where you need to optimize your code in order to get a better runtime or to fit in a certain complexity. So this is why we are using this unordered map and unordered associative containers. I will explain a little bit more into detail into the next video. Right now, let's keep it basic. We will write a code and see how the unordered map takes our input. Okay, coming back to our recap. So this is how we learned so far that a map works. In the case of unordered map, we have no idea how the output would look like, because here it doesn't matter if we just insert A, B, and C, or if we insert, let's say, B first and C later, and it just doesn't matter. They will be sorted, and that's just a guarantee. If we have an unordered map, so I'll write just here unordered map. Again, right now, the how we enter the keys, the order that we enter the keys doesn't matter. So the output can be very chaotic. For example, we can introduce A, B, and then C, and then if we go through the map, the first element might be B, the second element C, and the last element maybe A. Let's add a couple values so we always remember that for a key we have an associated value. So this is everything that you need to remember on this subject so far, that it doesn't matter the order that we introduce, that we put that we have our input arranged, the output will have all the elements that we insert with their certain values. They just will be in a totally random order. So let's see this in code. Let's see how this behaves. We will write as usual a very quick and quite simple code, sorry. Okay, including IOStream for input output, including the unordered map, ordered map from the STL, and a string. Do we want it? Yeah, let's also include a string. As always, the standard namespace, and right now into the main function. So let's do it straightforward. Let's read a string of characters str, and right now let's beautify it a little bit. Cout, enter a beautiful word, and a space, and let's now create our map. So an ordered map of characters and ints, and let's just call it M as usual. And right now we have to traverse our string starting at the beginning up until string.size ++I, and I think I've mentioned it before, but as a quick reminder, I'm inclined to use ++I instead of I++, because pre-incrementation increments the variable just slightly faster because it takes the reference of the variable. Post incrementation, meaning I++, copies the object, then increments it and returns that temporary object, and technically it takes just a little bit more time, so it's an extra feature to slightly optimize your code. Alright then, right now we will enter our character, so str of I is our character, and we will include it into our map. So it will also look like a frequency map, just in a completely random order. And in order for us to traverse it, we will, as always, do an iterator. I'm sure you remember how to do it. Iterator it, and right now should be very straightforward for you up to this point. We will stop by at after the last element of the unordered map, and we have to increase the iterator. Right, wonderful. And right here we want to print the character, and afterwards its number of appearances into the string. We will add an end line as always, and right now let's test it out. Everything seems right to me. Okay, just for I added this just for me. Enter. I think I already pressed an enter. let's run it again, and let's say more no, not a very intricate word. We actually say wonderful. Do we have any letters that repeat itself? Doesn't seem that. Okay, we will then write Annabelle. So as you can see, our print is the letters we got them totally random. Let's check a few of them. So we have A 2 times, N once, yep, B once, E 2 times, and L 2 times. Let's just try it again for the sake of the example. So we won't write an actual word, so let's say A 3 times, B a lot of times, D way too many times, and a couple of C's, and the Z at the end. And as you can see, we got them again in a completely random order. Alright, 21 D's, quite a lot of them. But we entered A, then the B's, afterwards the D's, C, and Z. So there's no rule whatsoever. This should not be a huge disadvantage for a lot of problems, but the time that is, for example, required for you to do a query or anything like that would be much faster than in an ordered map, because the main difference is that an ordered map would take n log n time to be built, because sorting it by default takes of n log n time complexity. So because we are eliminating this, right now we can keep everything under of n complexity. That's something we want to keep in mind, because at a lot of interviews, especially in the FANG group, meaning Facebook, Amazon, Google, Netflix, or Snapchat, or most companies, I've encountered this a lot of times. A lot of companies actually are looking for solutions that takes maximum of n time complexity. They are a little bit less harsh when it comes to memory complexity, because you can have very huge hard drives, and it's alright if you allocate a little bit more memory, but you just cannot make up time. So in a lot of problems, always keep in mind that if your algorithm exceeds of n, try asking yourself a few more times if you can just get it up to O of n. I know sometimes you might need sorting or something like that, which will go of n log n, but just try it and put yourself this question, because you might receive it, and you basically need to find a way to get rid of that sorting usually by implying using any other rule or trick that you might find looking at that data. And if you want to use a map and do it really quickly, like get the frequency of any item in a longer string of that item, so in a longer vector that contains items of that type, you can use it a map. You can use it an unordered map. I would actually recommend you to go for the unordered map, because you will get much better results, and there's actually fewer people that uses it, so it's more in your advantage to do it. Next time we'll also discuss another unassociative unordered associative container, and we will gather this more in depth. Right now, everything that you need to remember from this lesson, it's just what an unordered map does, and that it gets the complexity of our code much lower. So everything you will do in O of n. Thank you very much for watching, and I'll see you in the next one. Welcome back, everyone. In today's video, we are going to talk about the next unordered associative container, which is the unordered set. It is a very interesting and also important subject that would require you a little bit of attention when it comes more to its theory than to its actual implementation and code, because this will come very easy for you since you've already watched the set tutorial lecture, and everything is quite similar. In code actually it's identical, but it differs the way it's implemented behind the scenes, let's say. So let's recap a little bit again. What was the set doing? So we will cut this into two, but with a more beautiful line like this one, and I actually had the half right here. Yep, perfectly. And right here we will discuss the set, and right here we will have the unordered set. So basically what a set was basically an binary search tree with a certain data structure, and not just any binary search tree. It's actually an AVL, which means it will always be balanced. So a balanced binary tree, and it looks like this. So we won't have a tree like this, never implemented. Actually a set will never look at something like this. Will always be a root, and afterwards, actually no, I won't write any element because I don't know exactly what element I will have there before I have the input. So no matter how many elements are we introducing into the set, it will always try to make this binary tree balanced. And what is very important about this is that it's very effective. It's a great data structure, and if you remember from the previous lecture, it has one very important feature. It sorts the data. So we'll have our data sorted, and for example, if we want to do a query, so if we want to search, let's say this is a tree of numbers, then for example, let's say I'll have here 7, then 3, here I will have a 9, and then 1 and 4. Yeah, not the most beautiful binary tree that you've seen, but we can manage it. And for example, if we want to search the 4, we'll go from here to the left and then to the right. So the complexity of searching for a number, we could call it a find function, would be log n, time complexity. This is what we will be needed from the set lecture so far. Right now, coming into the unordered set. So as we said, the set is implemented as a balanced binary tree. The unordered set is implemented as a hash table. And this is the most important thing you have to remember about it. You can also be asked at certain interviews if you are using the unordered set, how is it implemented, or why you are using it. And you are basically using it because this time, of course, the data is row input, will not be sorted. So we have unsorted data. And most of the operations that we do in an unordered set usually takes off one time complexity. Find, insert, anything. So as here most operations took off log n, here everything takes off one, almost everything of course. Insert and so on. You can take, I won't be adding all of them again because you already have them in the set lecture, but every single method or function that had off log n time complexity in the set right now has off one. It's actually off one amortized complexity, which the worst case scenario, it is off n, that's true, but it's worth mentioning that in practice it can't be calculated with off one. It's an accepted measurement, so we'll take it as granted. And why this, before jumping into the code, let's just discuss one more time why this is important. Well, there's actually plenty of interview questions that you can find on any site or on the internet, any programming site or problem solving contest, and I've actually encountered this a few times in my career, where I've seen a lot of people, for example, they give you an easy quite easy request. They just give you some vector and then they tell you to do something basic, very basic about it. You might just need a sorting or something, so it will be n log n in order to have that data sorted, and then just a couple queries, searches or whatever, but it will not exceed of n. So the overall complexity will be of n log n in time complexity, of course. But in the end, you might have to get rid of the sorting, because as I've also mentioned in the previous video at an ordered map, a lot of companies are looking for solutions to their problems that have an overall maximum complexity of n. And that means that you are not able to sort anymore, and you have to find a way to optimize certain operations that you do on your data. And the best way to do that in a lot of cases is actually the unordered set. So as the map can get you out of a lot of issues, because that very quick frequency report that it does for you, it's staggeringly helpful. The unordered set will get you out of a lot of situations where you have to get rid of sorting the data, and you'll have to insert the data as quickly as possible, so in of one as in a normal vector. But then you can consider that if you want to find an object, it will also take of one. In a normal vector will take of n, which is a huge advantage for you. So in any problem that might just push you to the limit on the time complexity, or anyone telling you that your time complexity is too big, the first thing that should come into your mind is how you can use an unordered set on that set of data. As its implementation, actually as in real life code, it's just the same as the set. the methods are called the same. They are using everything is just the same, so it will be again very easy to implement. If you remember the set a little bit, this one will be just the exact same thing. Let's do a quick unordered set and see how it manages data. So as always, we'll start by including IOStream, the unordered set, and let's not do it on a string. Let's do an unordered set of integers, the standard namespace, and reaching our main function. Sorry, I think, yeah, right now it should be a lot better. Actually, the code would be very short. Let's declare our unordered set of integers as we have discussed, and let's just let's ask for an input. Enter how many numbers you want to add into the set. Scene length, and we will declare here an integer length, and a very quick for loop, as I've got you used to it so far. Alright, we will also need an extra variable and temporary variable. We will read this temp and then insert it into the unordered set. And right now, because we have the hash map implementation behind the unordered set, so it will create a hash table. We can do a couple of methods to see how it works. So we can just print it just for the sake of the example, unordered set, but nah, it's way faster if we just do a couple searches. So cout the number that you want to search. Enter the number that you want to search, and we will ask for this number. We can use our temp variable, we won't need it anymore. And then if s.find of temp is different than s.end, which is again sentinel after the last element of the unordered set, as for any other STL container, then we have find it, and we can just print found. Else, let's copy this and print not found. Okay, let's run it really quick. So we will do 5 numbers, 2, 3, 4, 9 and 0, and we want to search for 1, and it is not found. And if we, let's say, only bring in 3 numbers, so 1, 2, 7, I really like these numbers, and we want to search for 1, we have found it. So for example, even if we had, let's say, q number of, so let's say we had q number of queries that we wanted to perform. So we had q numbers that we want to search if they are found in our set or not. Here it will take us O of q or log n complexity. Actually, yeah, q log n complexity. Here it will just take us O of q. And if q is, I don't know, give a number, it's quite a small number, you can just consider it O of 1 as well. So this is why this data structure is very useful, and you should always remember this container, put it an asterisk, mark sign, because you can perform extremely well out of interviews by having all of these containers in mind. So if you need your data sorted, then okay, directly think of the map or the set and which one would benefit you better on what you want to achieve there. If you need if time complexity becomes an issue, then you can also consider an ordered map. If you also have to count for each object, you have to have a counting variable, or to, I don't know, get it associated something else. And the same thing applies for the unordered set. You want to find something to insert, you have a lot of let's say operations. Every single problem, actually, here's the tip. Every problem that tells you that you'll have a set of data and you will need to apply certain operations on it, it's definitely a data structures problem. So if in a problem you need to find and insert elements as quickly as possible, an order set is your best friend and will always be one of the best solutions that you might come up with instantly. So thank you very much for watching again, and I can't wait to see you in the next video.